Thank you. Thank you for all who chose to return for the second part, machine learning. Trust me, it gets much more exciting. We have to go through all the data cleaning and at this point, we're still talking about selecting features before we even start training. But this, I'm positive this lecture is will be a little more stimulating. There'll be more concepts here to deal with. All right, so let's, there's a bit of lag there. Oh, there's the contact. So you guys feel free to schedule office hours with me. They're usually at noon most days. I'll be open. Otherwise, I'll just use that to read papers. Okay, so this week it's all about feature selection, and we'll just jump right to it. We're going to spend 2 weeks on classification and regression next time. So, okay, so what is feature selection? I'm going to minimize this talk here. Yeah, so feature selection is basically what it sounds like, right? You have a variety of features in your source data, and you have to pick and choose which ones are going to be useful, right? And so you really want to limit the number of features you have. So sorry about that. I keep doing that. So the whole name of the game is to quantify what we mean by that, right? What we mean by useful. And we try to be rigorous in the way we define it there, and you'll come to learn that there is a whole spectrum of feature selection methods out there, each one's with their pluses and minuses, and I cannot possibly cover them all, but I hope to give you a good overview of the landscape. But this is also one of those deep rabbit holes. Okay, so why would we want to do any feature selection, right? Like if I have, you know, the more features I have, the better, right? Like why would I tie my hands behind my back, right? Well, I can think of 3 big reasons. The first is that with more parameters, the likelihood of overfitting is just higher, right? We're going to be talking about this concept of parsimony in a bit, but the idea is that you want to use the least number of variables to explain your data effectively, right? It's kind of like Occam's razor, right? The simplest answer is the best, right? So when this is just going to help you how generalizable your model is. Okay, the other is that, well, if the model has less features, if it's easier to train, it's going to be faster to train, right? And finally, so the more features your model has, the harder it is to interpret, right? That's kind of like why I put this is the parable, right, of the blind sages and the elephant, and each one is like touching a different part of the elephant. They come to different conclusions because there's so many features, right? Also you'll find that generally the more features you have, the less accurate your model will be. And a kind of a way to wrap your mind around that is like, say that you are trying to come up with a policy, say that you're some government official trying to come up with a policy, and you have to decide on how to deal with, let's say, crime in a certain neighborhood. So there's 2 extremes you can take. One is you invite everyone that lives in that neighborhood into some sort of like town hall setting and do a sincere job to listen to everyone's like concerns, right? To take to heart what they have to do and try to please everyone, right? And the other extreme is you say, I'm only going to hire a panel of experts, and they'll give me some very focused, some very focused insights into how to deal with these issues, right? So you can see how that small panel of experts maybe have their own internal biases. Maybe they're also politicians. Maybe they have their own biases. And in the other extreme, with if you invite every single person, you're going to have to make compromises just to please everyone. So the odds that, so it's going to be less likely that you'll make a good choice, right? Like you're just going to make a mediocre choice that tries to satisfy everyone. And yeah, with the panel of experts, your model is more biased. So those are kind of like the big reasons why you want to do feature selection. Feature selection sort of like is a way to systematically or programmatically find the middle ground between those two extremes. Okay, so feature selection falls, I would say, into 4 plus 1 big categories, and I'm lumping in mapping methods in there too, although technically they're not feature selection. Anyway, they'll fall in 2 big categories. The supervised methods, how I have written here in green, these are going to look for patterns in the data without considering the outcome, the labels, right? So we'll call these like the unsupervised methods. And the methods here in blue are the supervised methods, right? They take into consideration what the outcome is, and they fall into these 3 categories. You could kind of think of them like shells of complexity. At the bottom, you'll have filter methods, and it's basically a univariate analysis. Above that, you have what's called wrapper methods. And these, they'll use a model to, they'll use a model with a certain number of features in it, and you're going to add or subtract features into this test model and then gauge its performance. And then based on how it does, that informs your decision making on whether or not to include features. And the third method is they're called embedded models, embedded methods. These are just this is just feature selection that happens naturally as part of the model itself. Like the big classic example is lasso, which we'll talk about later. But these are like machine learning algorithms that naturally do feature selection. All right. Okay. So let's talk about unsupervised methods. The simplest of which is just correlation. And I'd like to start here because it emphasizes a very important point, especially in our field, when it comes to related features. So the idea behind removing correlated features is that, well, if 2 features are highly correlated, then by definition, knowing something about one will tell you something about the other, right? You can say that one is redundant, right? If they're both encoding the same information. And so a lot of methods, especially the linear methods, they do poorly with correlated features, what they call collinearities, right? There's a big push to remove collinearities in the features that go into your model. So from a predictive analytics point, this is a good thing, right? This is actually an easy thing to do, right? To remove correlations. But practically, it isn't. And for us, it's because, well, let's just talk omics, right? That if you have, so I study metabolomics, right? So if you have correlated metabolites, it's because they participate in some common pathway, usually is the case. And so if you're going to do your machine learning, to find those omics that are correlated, that are associated with your outcome, you can certainly do that. But then go on to say, of these features that I found were associated with my outcome, how are they related biologically? Well, that's a level of abstraction that the machine learning method was never intended to do. In fact, the machine learning method is only finding those features that are predictive. They have no obligation to represent anything in nature. They have no obligation to represent any biology. They're just merely predictive. And so to then do some sort of like pathway analysis or some kind of, you know, some biologically meaningful meta-analysis on the features that you discovered with your machine learning is that much harder, especially if one of your first steps was to remove all the correlation. So this is a careful balancing act that like you have to consider when you start designing your machine learning pipeline. And a lot of this just comes down to your domain expertise. So this is kind of like a really important point. So is there any questions to this? This is kind of like a deep philosophical point. Take a moment to pause. Everyone's sort of comfortable when I say like the metabolome are just readouts of the proteome, which are readouts of the transcriptome. We have that omics are naturally layered. Okay. All right. So lesson of the game: don't remove all your correlations. You'll make your life harder. Okay. So another unsupervised method is clustering. We're unfortunately not going to go into any detail other than this one slide, which is a pity. But clustering basically is all about finding patterns that naturally occur in your data, right? Like you're going to make these buckets and you're going to put your samples in these buckets. And in sklearn, I encourage you to like dive deep. They have many clustering routines, right? And what I'm showing here are in the rows. These are just test distributions of like sample data, right? Like here we have like the bullseye data. It's like two concentric rings, nested C's, correlated features and uncorrelated clusters, tight clustering, and this is just random noise. And what the clustering does is assign labels to collections of points, and they all do them in their own unique ways. It really is a pity we're not going to get into clustering. We can't fit it in. So if you have any questions, now's the time to ask me anything about clustering, or if you still have these burning questions, feel free to like contact me at office hours. But I'll give you guys an opportunity. If any questions on clustering so far? All right. Yeah, so the name of the game of clustering is just assign labels. Okay, so here I'd like to introduce you to a classic machine learning data set, right? Many of you maybe have heard of this before. It's the MNIST data set of handwritten digits. It's something like, it's tens of thousands at least. I know the training set has like 60,000, something like that. 60,000 samples of these handwritten digits. They were collected by the US Postal Service. And what they are is just, they're images, black and white images, 28 by 28 pixel images. And what we're looking at here is just a sample of them, right? Like these are a bunch of zeros, these are a bunch of ones, twos, threes, fours. So I'm mentioning this because we're gonna use it in a lot of the examples coming up. But yeah, so the image is just a 28 by 28, and you could think of each pixel as a feature. of which there'll be 784 features, and they're either on or off. And they're either on or off, and we of course have the labels, right? These are all zeros, these are all ones, these are all twos. Later, when we talk about feature engineering, you know, they don't necessarily have to be the pixels. They can be like the edges, the corners, you know, blobs or even enclaves, like does it have a hole in the middle kind of stuff. So let's dive in. Let's look at this in this data set, and let's look at some mapping methods. All right, so this is the next major class of feature selection. It's dimension reduction. It's not actually feature selection. What I mean by mapping methods is that mapping methods take your native features and transform them. They change their representation. Think of it kind of like, you know how some problems, like if I wanted to describe a circle, it's easier for me to use like polar coordinates rather than Cartesian coordinates. So transforming from like X, Y variables to like R and theta variables, that's a mapping, you know? And these mapping methods basically do that. So the t-SNE is probably like one of the most popular ones. And what it's going to do here is map. Sorry, I should take a step back and look at this picture. So in this picture, what I'm looking at is that very same MNIST handwritten data, handwritten digits data set, right? Where what you're looking at here are the labels. These aren't actually the digits. These are just the labels. They're actually points, right? And here are all the zeros, here are all the ones, here are all the fours. And remember that I said it's a 28 by 28 like pixel image, right? There's 784 features. Well, what t-SNE is going to do is it's going to take all of those 700 plus features and squash them down to two features. It's going to it's not a projection, but it's going to map all those features onto this plane. And it's going to do it in a very clever way that what they say is called it preserves locality. So in other words, what it means is that when two images, when they look the same, they'll tend to be close together on this mapping. And when they look different, they'll tend to be like pushed apart, right? So t-SNE is a way is a way to find these patterns in your data in a very well, I think in a very powerful way. So it's very popular, but there are two big issues with t-SNE. One, the process is stochastic, right? That means that the algorithm's like random. So every time you generate one of these maps, it's going to be different, even for the same data. Ideally, it'll be different, but it still shows the same structures. But in principle, but in general, it's I mean, you can't get the same map twice, and because of that, you can't use t-SNE to categorize new data, right? So that's one of the big limitations. You have to like put in all your data. You can't say I'm going to split testing and training and then do my testing with t-SNE and then somehow use that mapping on my test data. I mean, it just doesn't work that way. So although powerful, it has those two big limitations. So one of the ways to overcome that and introduce your own other set of problems is like a PCA, a principal component analysis, right? So what I'm showing here is it's that same data set. The labels they're not going to be zeros anymore. They're just going to be these colors. And I'm sorry about the blurry picture, but What I'm plotting here are the first two principal components. What that means is, remember I said like you could transform between like Cartesian coordinates, x, y, z, into polar coordinates like r, theta, and phi. PCA is something like that. It's a one-to-one mapping. So I have those 700 plus features that describe the pixels, the native features, and I transform them into this new representation, right? We'll get into what that is in a second, but all I'm plotting here are those two coordinates, right? Like r and theta, but not showing you phi, right? So what this is actually a projection. So I'm only showing two coordinates here, but all the other 700 plus of them are going to be squashed down, right? It's a projection. You're looking at them head on. And the result is that, well, often everything looks like it's on top of each other, right? But really, these 2 points that look close together here, maybe are really far apart in all the other 700 plus dimensions. And so that's one of the big limitations to PCA, that the projection doesn't preserve locality. So that's kind of like kind of like an important point here. So like if anyone doesn't understand what I just said there, I'm more than happy to like cover. Why is scikit-learn random state 42 is used when creating training and test set to avoid getting different mapping results? Okay, so that's basically your seed. It's a random seed, and if you use the same seed, you'll generate the same data. So when I said that it doesn't generate the same data, I mean, you could force it to generate the same data, but that means it's like the opposite of being general, right? It means it only works for this specific case. Yeah, and 42, I think that's just from Hitchhiker's Guide to the Galaxy or something, right? That's why they use 42. So this isn't like a dissertation or something on PCA analysis and how it works. But it's enough to know that the way PCA works is that it starts with basically the correlation matrix, right? The correlation matrix is just tells you how two variables are related to each other, right? And what it's going to do is transform that. We're going to diagonalize that matrix. So all you get is like values along the diagonal here, right? And with zeros everywhere. So if you could think of that kind of means like in this new representation, whatever that is, in this new representation, no two variables are correlated with each other. You know, they're like perpendicular to each other. They're said to be orthogonal, right? Kind of like x and y. X, y, and z are like orthogonal to each other. So it's a way to come up with a new representation where each element is its own, what we call a mode, right? The values, we don't need to get into too much into it, other than like the values that are along this diagonal, that like they add up to 1, and that if you add up the first few principal components, those eigenvalues will tell you how much of the variance is explained. So here I'm showing you like the original image made up of all 784 components. But if I only took the first 154th components, I can generate an image that kind of looks like this. Look, it's a little blurry, but I'm explaining pretty much 95% of the variation in all the pixels for all labels, right? These same 154 components will generate all the 6s and all the 0s and all the 4s. And of course, the fewer components you have, the less variance you can explain. But depending on your problem, however much variance you're comfortable with explaining, you can reduce the number of Well, dimensions that are needed for your problem. So this is what we mean by dimension reduction. We've turned a 784 variable problem into a 59 variable problem. Okay. Question about PCA. Is locality preserved within components? If two samples are close to each other on PCS, is that meaningful? No, no. If you have more than one axis, if there are, you know, n different components that you're not projecting, because you could only show 2 or 3 components at a time because we can't see in 4D or higher. You have no clue if they're just being projected on top of each other or not. In other words, if my first 2 components explain a very large percentage of variation, do we approach preservation of locality on PC1, PC2 plot? Yeah, no, that's a good way to like sort of justify it. Yeah, if your first 2 principal components explain most of the variation, then, well, by definition, that's where your data is distributed. And so you can feel comfortable knowing they really are far apart if they explain most of the variation. That's not the case here, obviously. With, you know, with 59 components, you still can only explain 85. That is a very good question. All right, so the workhorse of dimension reduction, of course, are encoders, right? So just like we just saw here with PCA, that with 59 components, we could explain a certain variation. Encoders do the same thing, right? They take a lot of features and try to distill them down, right? Think data compression, right? In data compression, what are we doing? We're really just removing the correlations. We're trying to express the data as succinctly as possible. And the way encoders, at least for us, the way they're going to be implemented is with a deep network. We're not going to get into today the nuts and bolts of deep networks, but it's suffice to say right now that an encoder, a deep network encoder kind of has this shape, right? This trapezoidal shape. So here, what I'm showing is that maybe your input data is like 100 features, and each layer of this network is going to sort of reduce the number of nodes, of features that it uses to encode that data. So you can gradually scale it down until eventually you get something like really small, right? So in here, I'm transforming this 100 feature data into like 2 variables, right? And then usually what's done is you'll make your predictions on those 2 variables, right? Yeah. So these compressed features, they're often called latent features, right? Or the encoded features. It's a short. In the series of these like lectures, I'm going to use this trapezoid as a shorthand for an encoder, and the inverted this inverted trapezoid to signify a decoder, right? And it kind of has the shape, right? It takes a lot of features and turns them into fewer. So one of the classic sort of setups that you'll see is what's known as an autoencoder, where you take your input features, distill them down into these, you know, important latent features, and then use those to decode them again. It's kind of like exactly like data compression, right? You compress your video file and then send it over the net, and then someone decodes it, and then hopefully recovers the same input. When we have this setup, well, I mentioned it's called an autoencoder, but it's important because, well, you just generated data. Do you get what I'm saying? You can take real data and create tons of generated or synthetic data, and that has a number of applications. Not least of which is just to, you know, beef up your training set. But yeah, there's like other more meaningful things you can do with autoencoders. Okay, so any questions so far? All right, so that's it for mapping methods and the well, the whole setup of unsupervised feature selection methods. Now we're going to talk about the big three supervised methods. The first, remember I said there were like layers. The first are these filter methods. This is basically a univariate analysis. What it's going to do is going to take each feature and compute it, like quantify its association with the outcome, right? Fortunately for us, that table 1 that I showed you last time does all the statistics for you. So that's exactly what I'm showing you here. Oops, sorry, I keep clicking. I'm sorry about that. So the easiest and most straightforward filter method is to simply select those variables that are significantly associated with the outcome. So in this case, we would choose age, not choose, I'm assuming this is systolic blood pressure. I don't know what that A is. We wouldn't choose height, we wouldn't choose weight, but we would choose whether or not they were in the ICU. Or if they were, we wouldn't choose if they were on a ventilator. So arterial, yes, thank you, Simon. Are they going to dialysis or something? I don't know. Anyway, so this is the simplest filter method you can do, right? It's basically univariate analysis and just pick those that are associated. These are the ones that like have anything to do with the outcome, right? The next method are these, or what we call these wrapper methods. And in wrapper methods, we are going to have like a prototype model. It could be anything. And to it, we're gonna add or subtract features to include, and then monitor how it performs. So the sort of the grandfather to these kinds of what we call stepwise selection methods is called forward stepwise selection. In other words, we're going to add. It's an additive procedure, and I'll walk you through it. So it starts with a univariate analysis, right? You get the p-values for all the features, okay? And then you ask the question, do any of them have a p-value that is less than 0.15? Notice that it's not 0.05. It doesn't have to be exactly like significant. It just has to be like have a chance to be, right? So do any of those features have a p-value less than 0.15? If not, then you stop the feature selection, and you've actually selected no features. Nothing's associated with your outcome. If yes, if there's at least one that's associated, then retain it, right? Well, actually retain the one with the lowest p-value. Okay, so now what you do is you're gonna now do that same kind of like univariate analysis. It's not univariate because now you're going to adjust for that retained feature, right? So if we had n features to begin with, we now have n minus 1, right? Because we selected one. So now we're going to train n minus 1 models and calculate the p-values of those features. If none of them have significance, then you stop and you've only selected one feature. But if there is something still significant, then go ahead and keep the one that's the lowest value and add it to this list of retained ones. And now you're going to train n minus 2 models and select the p-values, you know, and select them by p-values again. You do this over and over and over until nothing's significant anymore. And now, in principle, what you have left with are all those retained features that were significant. So, yeah, this is kind of like the method that started it all. Does anybody see any problem with this? I mean, I wouldn't say this is the method that started it all without sort of alluding to that no one does it this way anymore, right? Can anyone see any problem with this method? And you should know the answer because we've sort of covered it in the last two, well, in the last module, actually. Any takers? All right. What if features are related to each other? Maybe the solution will fill not fine. That's true. It suffers from, if you have correlated variables, it has problems selecting either one or the other, or if it's supposed to be both of them, That's a good point, but that's not its biggest flaw. It p-hacks, definitely. Does this, I sort of purposefully, yeah, 0.15, right? I sort of purposefully like arranged that like this. It's sort of supposed to echo that guide to p-hacking diagram that I showed you. So what are we doing? Run your analysis. Are the p-values something you like? No? Okay, well then do something like do it over again, check other ones, you know, and do it until you get an answer that you like. You're first of all, you're multiple testing. Yeah, and second of all, yeah, this 0.15, that is so arbitrary. Like why this number? They used it, it has some history because it works is the short answer. But from a statistical footing, it's actually quite poor, right? That's one of the reasons why people don't use it. Any given feature will have to be compared to outcomes and evaluated many times. Yeah, exactly. We're not. There's no place in here where we adjust for multiple comparisons. Sorry, multiple testing. I'm sorry, guys. So one of there's kind of like two ways we have gone to improve, like make it stand on footing. Remember we said last time that like this sort of iterative pattern is kind of a necessary evil, right? And given that we kind of need to do it, but it's statistically a big no-no, one way we can get away with it is with introducing like that validation set, right? That was that in-between set we used while iterating, so that you have the freedom to iterate a few times. So that'll get you part of the way. And so people will make like a k-fold cross-validation in here to help you along. But remember last time I said that validation set is precious, right? You only want to use it a few times lest you start being trained. And if you have, I'm sorry guys, and if you have like even 20 features here, that means you're going to go around 20 times. You've already broken that. So no validation set's going to help you like that. Another way that people have gotten this to like not cycle so many times is to penalize the number of features. So instead of using like the p-value, like the strict p-value, often you use what's called the Akagi information criterion. So that p-value, that's this log likelihood. And so like a p-value, like lower is better, right? So it just equally weights 2 times that p-value, but it's going to add 2 times the number of features you used. So the more features you use, this goes up, and it helps you break the cycle. Anyway, this is the grandfather of all wrapper methods. Don't do this. Don't do this, but it motivates a lot of the discussion that's going to come next. Any questions so far? Yeah, so the process, of course, can be done in reverse too. You could remove. It's functionally equivalent, right? You start off with all the values in the model and you remove them. And then, I mean, there's a ton of stepwise methods. Okay, so one of my favorite wrapper methods is Baruda. And I like it because it solves a lot of the problems that a stepwise method had. First, it stands on a more firm statistical footing. And second, it eliminates what Mert said, that arbitrary cutoff, right? So, so let me walk you through the way it works. So what you do is you have your features. These are your real features. And the first thing you do is you're going to sample what we call these shadow features. Shadow features is just basically that feature with all the values shuffled. So it's kind of like sampling sort of like a null distribution, right? Like all the samples, there is no pattern here, right? It's just completely random. And you do that for every feature. So these should be nonsense, right? And now you train a model. It could be any model. You train it with, sorry guys, we train it with all these features. Now you have twice as many features, but you train them with all of them. And now you look at, of these shadow features, which one had the lowest p-value, right? So we're saying if any feature now has for any feature to be significant, it has to have a p-value that's less than the best performing garbage like feature, right? That makes sense. So that does away with that first like arbitrary cutoff. It naturally tells you what the cutoff is. So yeah, so you use that highest feature to tell you whether or not any of these features have reached significance. And if they do, then you on the side over here, you're having a tally bar, right? And you're going to record how many times feature A met significance, right? So what we do is we're going to do this. It's an iterative process, right? We're going to do this many times. So every time you do it, the sample features the shadow features are resampled, and they're new p-values, and you're just going to accumulate. So let's say that I went around 20 times. Each one of these features can either have been a hit or a miss, right? A hit made like it reached significance or not. And because you have two outcomes, hit or miss, well, the statistics follows a binomial distribution, of which we know the statistics are well known, right? So that's what I have here. This is the binomial distribution for sampling 20 times. I'm sorry, guys. And so you calculate the p-value of the number of hits given that binomial distribution. And if it's less than 0.05, then you keep the feature, right? If it got 15 out of 20 hits, that's significant. And those features that were on the other side of the tail, you drop. And everything in between, Baruto actually tells you that it keeps them as tentative, but I also just get rid of them. I only keep the significant features. But this is a brilliant way. It's a brilliant way to do feature selection. And like I said, it's statistically sound. Any questions? All right. Okay. And is this the final one? No. So the second to last one. Now we're into embedded features. Embedded methods. So these are methods, like I said, the feature selection sort of just happens naturally as part of the machine learning algorithm. So one of the big two is decision trees that does this feature selection. Decision trees. So I'll show you now how decision trees work. We'll get into more detail when we do classification, but the way a decision tree works is you take all your data, right? Imagine that this is our data. It's only got two variables, x1 and x2. And these are our points. And these are our labels, squares and circles. You take all of your data and you're going to consider drawing a line, right? For every feature, for every value, for all values, right? So I'm gonna like start with x1, right? And then you say, okay, there's a data point here. If I draw a line here, and I split the data that way, like how disparate are those two groups? And by disparity, we mean something like the Gini coefficient. Maybe some of you guys have heard of like the Gini coefficient for like wealth disparity, or like showing which are like the richest countries of this and that. It's a metric showing how different two things are, right? It also accounts for how similar the two groups are, but never mind that. So it has a metric. Point is, there's a metric to describe, when I draw a line here, how different are those two groups, right? And different, I mean in terms of their labels, how mixed their labels are. And so yeah, we're gonna go through every point. So we go along the x1 axis, and you draw a line here, 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 here, and then you pick the one that was the best. But you also consider, you have to go through every feature too. So you also consider drawing along this way, a line this way, this way, this way, this way, this way, this way, this way. And of all those combinations, the line that gave you the biggest disparity, that's the one you choose, right? And so here I've just drawn it here that for us, it's that x1 equals 3 line. That's, I mean, it's a cartoon, but assume that this is just the 3 line. So if you're less than 3, you're on this side. And if you're more than 3, you're on this side. So I kind of like drew it like this. So here's x1 less than 3. Notice I drew them all red, right? It's kind of pure. And on this side, we're still kind of mixed, right? So I drew purple, right? So if your subset is all one label, you could stop that branch of the tree. If it's still mixed, you do it again. You consider every feature, all values. So you do it all over again, and splitting along x1, splitting along x2. At this time, it happened to be that x2 equals 10 was the best discriminator, right? And so you write it this way. So all those points that are above 10 here are red and it's pure, and all those below 10 are here and it's also pure. So now we can stop. So this is how like a decision tree sort of is built. This still hasn't done any feature selection. This is just in order to show you how feature selection comes natural to decision trees. I have to tell you how a decision tree works. Maybe this is a good point for asking any questions. Does DT split along one feature only at each decision, or multi-feature conditions? It's one feature at a time. Are there multiple, like the y equals x line, something like that? Like, I guess it could if you just draw a line, as long as it's linear and be on one side of a line versus another. I guess it could be. Yeah, I don't think I've seen something like that before, but I don't see why it couldn't. But yeah, generally it's just a long one coefficient. Has anyone seen it? Maybe someone out there knows more than I do. Yeah. Okay. So in practice, just like the forward selection, it's never done this way. And why do you think it's never done this way? Like, where's the bottleneck in this algorithm? It's right here. It's right here. Imagine if you had any substantial data set with, like, say 20, 30, 40 features and thousands of points. So it's going to be like 20 features times 1,000 points. Well, no, it's 1,000 to the 20th, right? Because you have to consider all points, all features every time. This is huge. So in practice, you can't sample them all. So what's done is, oops. So what's done is stochastic. I'm not going to go through all the features, and I'm not going to go through all the values. I'm going to pick, 3 features only, 3 random features, and cycle through all their values to draw the line. And that's fine, but because it's a random realization, you're going to have to iterate, right? You're going to have to do this again, and maybe next time when you start your tree, you'll pick a different 3 features, or maybe you'll pick a different 3 over here. And so each one of these realizations of these trees is what we call the forest, right? So this is what we mean by random forest. So now that I've sort of explained how like a random forest is built, now I can get to the part where I demonstrate how feature selection is done. So now that you have your forest, right, you can ask the question. Each one of those trees in that forest is a model, right? It's a model, and it has some accuracy. Usually you'll cut it off. You say, don't go too many layers deep, because if you let this go as deep as it wants to be, it would be 100% accurate. Basically what it means is like each one of these nodes at the end has only 1 data point, and models that are 100% accurate are useless. So anyway, so to maintain generality, you'll limit it to like something like 3 branches. You can only branch 3 times, and you have a random forest of like say 500 trees. Each one is a model, and now you can ask of those models. I go through the features one at a time, and I say, what happens if I remove one of those features from the model, right? If it was, remove it from the model, you can't use it, right? So the tree has to, you have to build a tree without using that model, right? That feature. Well, presumably the accuracy of that model is going to go down, right? And so those features that when you remove them, the accuracy, the mean accuracy of all those 500 trees, if the bigger the mean accuracy drops, the more important that feature is. And so that's sort of how we rank the features, right? This is how feature importance is expressed in a random forest. And you could quantify it by mean decrease accuracy or with the Gini coefficient, but that's how feature selection is done in a random forest. Any questions? Okay. All right. So the final method we have here is lasso. So lasso is a linear model, and it's what we call a regularized model. Regularized just means it's going to penalize some features in some way. So let me walk you through it. So imagine this is our data, right? The data is actually multivariate. There's feature X1, feature X2, feature X3. There's a bunch of them. Oops, I keep doing this. I'm sorry, guys. X1, X2, X3. I'm only showing X1 here, right? So because we have like a linear model, like y equals mx plus b, right? That weight is the slope of this line, right? And so you can now quantify the error with respect to this one variable, but the error is like how far off is the real point, the real value less your predicted value. That's how we quantify the error here. So now imagine that we took all these weights, right? They could be anything you want. And so we take, let's just say that there's 10, 10 variables. We can write that as like a vector, right? Or you know what? It's just a configuration of all those weights. And imagine that there is a space of all the configurations that those weights could possibly be, right? With any arbitrary configuration of weights, you can calculate that error, right? Measured as like maybe the mean error, the mean squared error, or the mean absolute error, whatever it is. you can, every configuration of W of these weights is going to give you a unique error, and it'll have this complicated shape, right? So now we can say this is actually like a gradient descent, but it expresses what the regularization is. The way to calculate the optimal weights is that configuration of weights that minimize this error, right? And so iteratively, the way you would do it is like you would start some random point and you look at the slope of this line here. So basically the change in error with respect to W, right? This like the slope of this line. You see how it like points down? It's like a negative slope. Well, that's what this is saying here. This is slope. I'm gonna want to take a step that is in the opposite direction of that slope. Do you see what I'm saying? So if the slope here, it's pointing down, it's negative, then I'm gonna want to go in the positive direction. So W is instead going to march forward. And so this ball is going to go to this point, right? And it's going to keep, and here you see how the slope is like positive, it's going up. Well, that means take a step in the negative direction. So it's going to go this way and this way and this way. And this part alone, right, that your new weight is going to be your old weight left in the opposite direction to where your slope is pointing. That's basically gradient descent. That process will take you to the bottom of this well until the slope is 0 and this says don't move anymore. The regularization is this term here. Notice lambda here is just, it's a number like 0.1, something like that. It's a number that is proportional to the size of W, right? So if W is big, then if this is positive, then it's going to say take a step in a negative direction, right? So it's going to, if W is positive, it's going to try to shrink it. If W is a negative number, it's going to go in the positive direction. That's where the negative sign comes in. Does that make sense? So this term here tends to push all the weights to 0. And in this case, this term here, since W is positive, it's going to try to push it this way. But this term will kick in because the slope is negative. It's going to try to push it forward. And when these two terms cancel out, then there's no more changing. So it'll rest not at the bottom of the well, but somewhere around here. That's if the error changed with respect to changing the weight. In other words, if this variable is completely uninformative, changing the weight isn't going to help you make a better prediction. Your error is not going to change. So for those variables whose slopes are 0, they're not informative, this term kicks in and drags them to 0. And that's how feature selection works. It's basically by looking at the weights. This L1 regularization is going to drive these to 0, and then the ones that have any finite value at the end of this process, those are your informative variables. Yeah, and that's actually the end of all the methods I have. So any questions at this point? All right. So yeah, at this point, I'm going to jump into the notebook. Please feel free to like ask questions if you want on the slides. Let me just pull up the. Oh, it's already there. Okay, let me pull up the notebook. Jupyter. All right, so today we're on the desktop. Yeah, so there's a homework and then there's a notebook. We'll be looking at this notebook today. We're going to see all of those methods that I talked about implemented in Python and sklearn. All right, so in distributed along with the module in this data folder, you'll find two CSV files called test and train. In them, they contain another classic data set problem, another classic data set. It's the mobile price data set. It's a set of 20 features. These are mobile phones, the features like their screen size and all that stuff. And the outcome here is their price, right? The price is actually, it's been binned to like, you know, cheap, expensive, and or cheap, like moderate and expensive, something like that. But we're going to just treat it like a continuous variable, although it's not. So let me describe the data for you, okay? So there are 2,000 observations. These are different phones, I guess, in the training set and 1,000 in the testing set, right? And there's going to be 20 features and one label. The features are battery power, whether or not it has Bluetooth, the clock speed, does it have SIM card, the megapixels on the front camera. I won't go through every single one, but the number of cores, the RAM, the screen height, the screen width, the talk time, like how long you can talk on one battery charge, whether it has 3G, whether it has 4G, and whether or not it has Wi-Fi. And then the outcome here is this price range. It's actually 4 values: low, medium, high, and very high cost. Okay, so I suppose I should just, first thing we do is going to just load up all the requirements. You don't really have to worry too much about this. I'll just go ahead and load them all up. And here is a really good place to ask, like, what are we doing? You know, what is the question here? Well, it looks like a classification problem, but really this is a feature selection exercise. So I really don't care how good the model is right now. I just want a way to compare the feature selection process yeah, there we go. I want to compare the feature selection process to well, no feature selection. So this is what we're going to call our parsimonious model. This is the model that has only the selected features, and the prodigious model. This is the model with everything, you know. And we're going to look at how well those two models perform. Okay. So so first thing we do is we're going to load up the data, right? The data, like I said, it's in that data folder. There's a training and a test set. And one of the first things you should do is just generate a table 1, right? It's going to answer a lot of questions for you. The data has already been sort of rectangular and cleaned. This isn't a data cleaning exercise, but it's still good to look at the data. Okay, so yeah, so here we are. Here are all the features, I've grouped it by that last column. That's the outcome, and here you see them, right? Like cheap, like moderately expensive, very expensive, and very expensive. And here we have the p-values, right? What is the association of this feature to the outcome? So right off the bat, you can tell that this is already like doing the filter of feature selection. You could do it that way. Okay, so yeah, like I said, we need a way to compare the models. You really don't have to worry too much about this because this isn't an exercise in training models, but I will go through what's going on here. So what I've done here is I've written a function here called compare models that's going to take your input data and a list of selected features, okay? And it's going to use those selected features to create a parsimonious model, and of course use all the data in the data set to create a full linear model, and we're going to compare them, okay? So this, like, I think this is the first time we use sklearn, right? I try to keep the sort of the same conventions, naming conventions that they do, but first thing you want to do is you want to get your predictors and your labels, right? This, when you build these models in sklearn, that's what you need, is X and Y, right? So that input data, I'm gonna basically drop the price range variable. That's the label. So give me everything except for the label, and then quite the opposite for the label. Just give me the label column, right? The target column. So now we have our X, Y. We need to find out, we need, sklearn is all based on like NumPy, right? Whereas right now we're working with like data frames. So the labels are going to get dropped, not the labels, the headers, the column names are going to get dropped. So this is why I'm getting the column index here. So I take that the predictors, I get the column names, and I'm doing a bit of anyway, I'm pulling out the index here. So remember the syntax from module 1 that says like for the feature names in the selected feature list, if that feature is found in X in that data, then give me the location, give me the index of that feature. And so what you'll get here is a list of the feature indices. List comprehension is the word I was trying to like say, the spacing out. Anyway, so internally here, what we're going to do is we take that input data and like I'm going to do a 70-30 split, right? This is separate from what's going on in the rest of your analysis. Like in this function, it's going to take your input data and it's not going to just predict on the input data. It's going to do proper partitioning. So of the data that went in here, I split it. In sklearn, the function is called test train split, right? You put in your predictors and your labels, and you tell it what's the fraction for partitioning. Notice here there's a random seed. Okay, so now what you'll get at the end of this is you're going to get your predictors, your training predictors, and your testing predictors, and your training and testing labels. And now we are going to define a model. It shouldn't say logistic model, it should say regression. Okay, so what I call the prodigious model and the parsimonious model, they're both linear. It's both linear regression models. They need to be the same or else I can't compare them. And then we fit them. This is the training, right? So the prodigious model is going to be trained on the predictors in the full data set and the labels, whereas the parsimonious model is going to get trained using only the selected features of that training set. Does that make sense? And the labels don't change. So now we've trained the prodigious and parsimonious model. And then finally, we just report some kind of error. This linear regression has a method called score. And score is basically the goodness of fit, like an R squared, right? 1 is perfect and 0 is terrible. And that's what we're gonna output. Yeah, it's the R squared. So yeah, so it's just gonna just report what the two scores are, and then we can compare them. Okay, so let's try the filter method, right? So if we look at the table 1, we can look at the significant features, right? Those are the ones that are p less than 0.05, right? We can look back up here, but it's what? Battery power, internal memory, mobile WT. What is mobile WT? Let's look it up. Mobile WT. Oh, the weight of the phone. Yeah, I guess people want light phones. Are phones getting smaller? Yeah, they are, right? Pixel height. So I guess it's your screen. How many pixels high is your screen? How many pixels wide? How much RAM is in your phone? Not that. Anyway, so you do what I just did, right? And then you list them. I hope I got them right. Battery, internal memory, the weight, height, width, RAM, and screen height. Did I say screen height? Not really, but I'm not gonna change it. It wouldn't have made it past this list. But yeah, you select your features and you stuff them into that function we made. So DF is our training set. Right, we loaded up the training set here. Yeah, DF is the training set and DF test is the testing set. So don't confuse that with this 70-30 that's going on in here. That's all internal. I'm only passing it training data in here, and it's going to do its own splitting. You want to save that testing set, okay? Don't touch it. So anyway, you put it in, and let's see what the outcome is. All right, so it says here that the prodigious model had a score of 0.91. That's pretty good. And the parsimonious model actually a better score. So what was it? 1, 2, 3, 4, 5, 6, 7. Yeah. So with only 7 features, I was able to even do better. Right. That's kind of like demonstrating how if you throw everyone in there, you're gonna have to make compromises. All right. Supervised methods. So correlated features, we want to remove them. Okay. So this is pandas. Yeah, this is pandas. You could use a core function in pandas. So if you call core function on a data frame, it's going to generate a correlation matrix, right? And you could plot that with Seaborn. I think we did this like two modules. I think Simon did this, right? Correct me if I'm wrong. Made a heat map. Anyway, yeah, let's just look at it, right? Yeah, here we go. So along the rows here, you have all the features, and along the columns, you have all the features again. And along the diagonal, the correlation with itself, by definition, is 1. And you can see that some features are correlated, right? I mean, correlated is relative, but pixel width, for example, is somewhat correlated to pixel height. That makes sense. If it has 4G, it has 3G too, you know? We didn't make a heat map, we just wrangled the correlation matrix. Oh, okay. Well, now you can visualize it with the with the SNS thing. So PC, FC. Oh, the primary camera and the front-facing camera, they're correlated. I guess it's likely they'll have both. I don't know. So what you could do is you see how these are correlated, right? And I choose a random. Oh, the RAM is very much correlated with price range. I guess people want phones with a lot of RAM. We can loop through those columns and keep track of the features with a correlation. I chose a cutoff of 0.5. I did this only because to select anything for demonstration purposes, but in practice, a more reasonable cutoff for this correlation is something like 80 or 90%. In other words, if features are like 90% correlated, one of them is redundant, like without a doubt, right? When they're 50% correlated, I mean, you're probably throwing the baby out with the bathwater there. Nevertheless, I chose a cutoff of 0.5, right? So the way you implement this is like you'll create an empty set, right? This empty set is where I'm gonna list my correlated features, and I'm gonna loop over the pair of features, right? So for the number of columns in the correlation matrix, less the label, just march through them. These are indices, right? Index 0, 1, 2, 3. And then J goes from 0 to I. So I'm only doing like the lower triangle of combinations. So J is strictly less than I, right? And I just look at that combination, the correlation matrix at element ij. Is it bigger than half? If it is, then get that column name, of that feature, and then add it to this empty list, and march through. And at the end, you should get a list of correlated features. And so we do that, and it finds FC, 4G, pixel height, and SU, screen height. This is the name of the feature that is correlated with at least one other feature by 50% or more. Does that make sense? What I did here, and notice I used set. Set means like each one of these is going to be unique. So this found 4 correlated features. So we could just go ahead and remove them, right? So I'm going to do this again. Compare the models with my selected features, where the selected features are going to be all the features in the data frame less, these correlated features. And I'm going to go ahead and add price range, the label, to the features I want to drop, because obviously you want to drop the price range because it's in here. All right, so I do that, and the prodigious model should never change, right? It's still using all the variables, but this parsimonious model, the R squared isn't as high. And why? Well, because 0.5 is kind of brutal, like this correlation, and even then it only removed 4 variables. Like it still has most of them. So it's probably a terrible method with this kind of cutoff. The goodness of fit, yeah. Any questions so far with what I've done? So we've done the filter methods and the unsupervised, just the correlation-based method, and they're okay. And now we're going to get to like the wrapper and embedding methods. Okay, so in sklearn, you have what's called recursive feature elimination. Remember how I showed you 4 stepwise selection? Well, recursive feature elimination is kind of like the opposite. You start with all of them and you systematically eliminate features, but in principle, it's a stepwise method. Okay, so you don't want to do forward feature selection anyway. So the way you would call it is, recall that wrapper methods have there's like an intrinsic model. There's like a model that it's going to use to do its feature selection. You have to supply that here. So it's really easy to use. First of all, let's get our predictors and our labels again. And you just call RFE. I use the k-fold cross-validation method just to improve the statistics. But you supply the estimator. And here we're going to use a classification tree. Notice that our model is this model that we're comparing. That's a linear model. The model you use for your feature selection doesn't have to be the same kind of model. In fact, probably shouldn't be. So yeah, so here I'm defining a decision tree classifier, and you instantiate it here, and then you just fit it with your data. Once it's all fit, you can output like how the feature, like how it ranked the features using the RFE support and RFE ranking. So support is going to tell you whether or not it was selected, and rank is just, well, it's going to rank them. All right, so let's look at this. So remember, these are now I've lost the labels, right? They're just columns now. But it says here, like the zeroth feature was selected, a rank of 1, so it's really good, you know. And it selected a number 11, 12, 13, and that's it. So it selected 4 features. So 0, 11, 12, and 13, great. So those correspond to battery power, pixel height, pixel width, and RAM. Okay, so we could build a model with only using those 4 variables, right? So here are the indices, and I can select those columns by their index. So these are my selected features, and I stuff them into that compare models function that we made. So you see the parsimonious model is as good as the prodigious model, which is kind of great because this prodigious model has 20 features, and this one has only 4. So that's great. All right, Baruda. So it's one of my favorites. So I like it because it's usually faster than RFE, especially when you have the more features you have. It's gonna get a lot slower than RFE. And for these like stepwise methods to have any stand on any like statistical ground, you need to do some internal cross-validation, right? Like repeated k-fold cross-validation or something like that to boost its statistics. And that means just training that many more models, it makes it that much slower. So so I don't know, I can't sing the praises of Baruda more. You implement it in a similar way. So we get our predictors and our labels again. And just because it's an embedding method, it needs a model, right? Here we're going to use a random forest classifier. Okay. Don't worry about this. This just means that I only allow it to go 5 layers deep. But yeah, you just define your model, fit it, and then use Baruda Pi. That's the method that does the feature selection. Baruda Pi, you put in that model you just trained, and I think these are the default values, but number of estimator is automatic, so automatically figure out how many features to select. Verbosity here is like 0 means it's not going to output anything, but you can track how its progress, and sometimes that's useful for debugging. And of course, it's a stochastic method. So you put in a seed, and it's going to select these. Well, it's going to make this object that is what does the feature selection, right? So you fit that with the data, and I just print out again, you know, the rank and the support, right? Support is going to tell me whether or not you keep it, just like we did with the recursive feature selection. So never mind the errors. These are because it hasn't been updated, the Baruda, for the latest version. So don't worry too much. Oh, it's still running. Geez. Okay, there you go. I think it just finished. So I guess it's slower when the number of features is small, like 20, it's slower than recursive feature, but trust me, when number of features grows, this is a lot faster. So what did it say? It said, let's keep battery power, and we're going to keep pixel height, pixel width, RAM. These are the same ones. Yep, they're the same features. So yeah, it picked the same one, so I don't have to, you know how the models are going to perform. They're going to perform, you know, equally. Okay. Any questions so far? Oh, here we go. Why do we fit X and Y first? Isn't fitting part of the Baruda workflow, and where we fit X and Y and shadow X? Okay, so you don't have to fit the shadows. It'll do it for you. And I think you actually caught you caught me. I don't think you need to do this. I think this is part of me when I was writing it. You define it, you define your selection, and then you fit it. So thanks. Where were we? Yeah. So nevertheless, it selected the same features, so that's good. And we know how they're going to perform. All right. Okay, so the last one is lasso, right? Many of us have heard of it. The implementation is going to look similar too. Here, you don't supply the model because lasso, it's an embedded method, it's its own model, right? So again, we pull out the predictors and we pull out the labels, and I'm going to do this. I mean, this is just fitting the lasso model. I'm using lasso CV so that I could do like 5-fold cross validation just to boost the statistics. But you just do that. You just fit it, and the model itself is the feature selection, right? So I'll put the score. I don't know why. You don't need to, because we're interested in the coefficients. So the importance, remember I said the importance are going to be the magnitude of those coefficients to each feature, right? And so what I'm going to do here is I'm going to make a bar plot, right? Well, bars for every feature, and the height of that bar is going to be this importance, right? The magnitude of that coefficient, and we can visualize the feature importance that way. So that was quick. Wow. So what did it pull out? Look, battery power is important. Pixel height, pixel width, RAM. Surprise, surprise. It's the same features. It's assigning some weight to the weight, yeah, to the mobile weight. So these are all kind of good. So you would do something like this. You would throw a bunch of feature selection methods when you're in your discovery phase, when you make your discovery set apart from your big training set, and you're going to look for those features that are independent of the method that you use to do your feature selection. These are the robust features, and sometimes you can start making some inferences, like based on your domain expertise, right? Like maybe these were some sort of like for me, they would be like metabolites, and I'd be like, oh, those are 2 metabolites that are part of the such and such pathway, like fatty acid oxidation, or I mean, what have you. And this can inform the way you design your final model, right? So so yeah, so in conclusion, yeah, I hope I gave you a good overview of feature selection techniques, how to use them, and like I encourage you to like dig into this model. I made some notes here. Notice I never used that testing set. I saved it and I kind of left it like left it there. So the idea is you're not supposed to touch it. So I encourage you guys now to make a model. It doesn't have to be linear. Make a model using the features that, you know, were the usual suspects, and see how it performs, validate these relationships using that testing set. Another big thing for those super achievers is notice in table 1, there were some errors, right? Or warnings rather. It said some things were like maybe multimodal or maybe not normally distributed. We didn't do any data cleaning, and you really should, right? You really should make all your data like normally distributed and address all those warnings, because the quality of your data that goes into these models is going to directly affect how good your model can do, right? Garbage in, garbage out. So I encourage you to like, yeah, see if you can't clean up the data. If you can clean it up, see if you can't get better than 0.91 was the prodigious model. So I'll leave that as an exercise. So in the last few minutes now, I'll go over the homework. It should only take about 5 minutes or so to get you, you know, up to speed and what we want you to do. But maybe at this point is a great place to stop and ask for questions. Anything I covered? How do I choose an appropriate feature selection method? So, yeah, so each one of these feature selection methods has pluses and minuses, right? So I encourage you to look up what they do, but I could say something like linear models, especially ones that employ some sort of regularization like lasso, will suffer from collinearities, right? If you have a bunch of features that are correlated, it's not going to select them all. It's only going to select one. And because if your feature selection method is something that's stochastic, like we're going to generate a bunch of realizations, there's no guarantee it's going to keep choosing that same one, right? Say there's 3 correlated variables, maybe one model picked one, another picked another picked another, and when you average them, it says, oh, this feature is only 1/3 as important as it was, even though every single time they were this feature part of this family was always selected, right? And so you'll miss it, right? Like if they were, yeah, like I said, like for me, because I always think of metabolites, right? If they were metabolites and they're all part of the same pathway, and at one time it's picking this one metabolite and the other another, as a whole, it's not telling me that that pathway is particularly important. So collinearities are a big problem with a lot of these methods. And so I guess to answer your question is, if you were to just throw these big 3 at them, that'll give you a good coverage. And what you want to find are, it's not about finding the best feature selection method. It's about finding the robust features, the ones that are independent of method. Those give you your best shot. Any other questions? Right. That was a great question. All right, let's I'm just going to close it without even shutting down. Let's do well, not do the homework. You guys are going to do the homework. So the homework is going to follow a lot of the beats that we just covered in here. Oh, here we go. So for the present case, would we look at the 4 feature robustly return and then eliminate PXP width because they're correlated or simply encode resolution? Well, yeah, I would do that. I would engineer, because we know something about, like screens, right? And resolution. Yeah, you would encode like engineer a new feature called resolution because they're correlated. Yep, absolutely. Yeah. So like this is one of those places where you have to inject your domain expertise. Definitely. All right. So for the homework, we're going to look at a new data set. All right, and I picked a doozy. So the PIMA data set, I'm partial to it. I also supplied a data description along with it, but very quickly, it's from the NIDDK, right? I'm in nephrology, so this is what we look at. And it's oops, sorry, I didn't mean to maximize it. And it's Native Americans, right? I think they're all female, and they look at these 8 features, and then they're diagnosing diabetes, right? So age, their plasma glucose, the number of times they've been pregnant, and you can find a data description here. I'm not going to go through it, but what I really want to stress to you guys is that this has missing values. So you have to do some tidying here. And also, this data file is, I guess, semi-structured, right? It is, what I mean by that, it looks rectangular, but it actually doesn't have any column names, right? All the headers. If I look at if I very quickly open this up, you'll see it's just numbers. It's just numbers. You have to come up with your labels or the column names, right? So do a little bit of formatting yourself. So what we want you to do is, first of all, clean up the data, and then make a 70-30 split and save some testing set, just like we did in the thing. And with that training set, I want you to compare the filter method, Baruda, and lasso. Choose the important features and then build a model. I wrote linear, but I guess you could do any model you want. I really don't care. And then compare, and then you know, validate it using the reserved testing set, and you'll just follow the same beats. So I think it's a fun project. It's a little diabolical, but I think it's fun. All right. Any questions? Yeah. Look at that. We're 10 minutes early for scheduled time. I noticed an additional assignment in data processing. Should we start that now? Yeah, you can do the data processing. That's fine. We're past the data processing part here. Image processing. Oh, definitely. You can hold off if you want. Definitely, you can hold off. We're not doing image processing till week 6. My week 6 module 6, 7, 8, 9, 10, 11. Module 11. Wow. Yeah, you have time. You have time, but certainly do it before then. I'm going to stop sharing at this point because I'm losing my voice. Any questions? Any other questions? I've lost the chat. All right, well, I'll hand it over back to Henry.
Okay, great. So if you haven't already, make sure that you do the Introduction to Supervised Learning with Scikit-Learn course in Data Camp. That's one of the assignments that we've given out. And make sure to do the homework for today. So if you finish that, please send it to us. You can email Dan, you can email Simon, you can email myself. We'll make sure that it gets to Dan either way. But yeah, preferably email Dan. And we'll make sure to go over that and give you feedback. So beyond that, if you have any questions or if you want to come to office hours, make sure to do that. Those links are in the syllabus, which is on the course website. And I think that's pretty much it. So yeah. All right. Any other questions? Okay. All right. Well, then this is going great. Let's regroup again next week and make sure to reach out if you have any questions or concerns along the way. Okay. Thank you all very much.
Bye.
See you all next time.